This is part 3 of the series Integration. We're going to start this part by looking a little deeper into the idea of solutions for differential equations. So we've done before the idea that differential equations such as this one up here, dy dx equals 3x squared minus 1, has many solutions. Each is a vertical translation of the other. If we're given just a little bit more information about the function, we can go beyond what's known as the general solution, and we can discover what's known as a particular solution to the equation. That is, which one of those vertical translations of the family of functions that are solutions to this differential equation are we actually talking about? This information that we're talking about is what's known as the initial condition. So let's say in this case that given this differential equation, we want a particular solution that passes through the point 2, 4. So this is our initial condition. The function is going to pass through that point. So let's begin by going ahead and taking a look at the antiderivative of this original function. Let's solve this differential equation. So we know that the antiderivative, or big F of x, is the same as saying y, because the solution to this is y equals some function. And we find that by taking the integral of 3x squared minus 1 with respect to x. So let's go ahead and differentiate or integrate this. So this is 3x, add 1 to the exponent, divide by the new exponent, minus x plus c. This is our y. And so what we have is y equals, these 3's cancel out, x to the third minus x plus c. Now let's use our initial condition. So we have a point 2, 4. So we know our x is 2 and our y is 4. So 4 equals 2 to the third minus 2 plus c. So this gives us, give ourselves a little room, 4 equals 8 minus 2 plus c. 4 equals 6 plus c. Negative 2 equals c. So our particular solution then is going to be y equals x to the third minus x minus 2. This is the particular solution, the particular vertical translation of the general solution of this differential equation. Let's go ahead and try another problem and see if we've got a handle on this. So in this problem, we have another differential equation, and this one, before we solve it, we're going to have to rewrite. And here is our initial condition, big F of 1 equals 0. So rewriting this, we're going to bring this expression up into the numerator. So this is x to the negative 2. And we're going to integrate this with respect to x. And to integrate this, then we have x to the negative 1. We add 1 to the exponent, x to the negative 1, over the new exponent, negative 1, plus c, which gives us negative 1 over x plus c. And that, of course, is equal to y, or we could have said f. And f of 1 is 0, so we put a 1 in for our x, so negative 1 over 1 plus c equals, and our y is 0, so then c equals 1. So our final particular solution is f of x equals negative 1 over x plus 1. Now, at the risk of being nitpicky about this function looks like this, very, very roughly. And so there's two sets of solutions, one for x is greater than 0, one for less than 0. So this is actually the solution where x is greater than 0. So it's inconsequential to the idea that we're getting at for the particular solution, other than to say that this is the particular solution on the right side of the y-axis. So let's go ahead and take a look at another problem and see if we can uncover some new information. In this problem, we're given that a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Now, this type of problem is characterized as a vertical motion problem. And so we're working with a different variable other than x. In this case, it's t for time. So we're going to be working with different variables, and it really doesn't matter what the variable is that you're using in your integration. It's still the same process, which we'll see in a second here. So let's start out by writing down what we know and then seeing if we can come up with this position equation. So let's go ahead and start with an acceleration expression. So acceleration with respect to time. In the Earth's gravitational field, we're dealing with either 32 feet per second squared or 9.8 meters per second squared. Since they gave us everything in terms of feet, let's use the feet per second. Now, acceleration, since we're being pulled downward, this acceleration is going to be negative. So 32 feet per second squared. Now, we have to take this and integrate this, because if you remember, the derivative of position is velocity, and the derivative of velocity is acceleration. Therefore, the integral of acceleration is velocity. So if we integrate a of t with respect to time, we're going to get velocity with respect to time plus some constant of integration. So the integral of negative 32 with respect to time is negative 32 t plus c. And this again is our velocity with respect to time. Now, they gave us an initial velocity of 64 feet per second. So at time t equals 0, our velocity is 64. So 64 equals negative 32 times 0 seconds plus c, which means that our constant of integration here is 64. Therefore, our velocity function, the particular solution to this differential equation, is negative 32t plus 64. So now that we have our velocity function, we can integrate it again and we'll get our position function. So we know that s of t equals the integral of v of t with respect to t. So s of t equals the integral of this, integral of negative 32t plus 64. Run out of room, so let's give ourselves a little bit of room. And never forget, we must use the variable of integration here. So s of t equals negative 32, pull out the constant, add 1 to the exponent, t squared, divided by the new exponent, plus 64t plus c. Now let's simplify. This gives us negative 16t squared plus 64t plus c. And this is our position. And remember that they said we had an initial height of 80 feet above the ground. So at time t equals 0, this position was 80 feet. So this is our s of t here, so let's rewrite that. And it's 80 feet when t equals 0. And as you can see, our c is simply going to be 80. So our position function, s of t, is negative 16t squared plus 64t plus 80. So there's our position function, and that's what we were looking for in part A. And in part B, we're asked, when does the ball hit the ground? Well, let's go back down to our position function, and the ball hits the ground when the position is 0. That means when the ball's height above the ground is 0. So we say 0 equals negative 16t squared plus 64t plus 80 equals 0. And now we solve this quadratic. And that should be fairly straightforward because the numbers work out fairly cleanly. Let's pull out a negative 16. And we have t squared minus 4t minus 5. So we can go ahead and factor that. And that gives us 0 equals negative 16. And we have two linears, t and t, plus and minus. Looks like this is going to be a 5, and this is going to be a 1. T squared minus 5t plus t minus 5. And there you go. So we know that t equals negative 1 and 5. Obviously, we can't use the t as negative 1. So our final solution is the ball hits the ground at t equals 5 seconds. All right, well, let's move on to the next section and see what's in store for us.